So as I mentioned, for WebGL, we are going to use shaders. So shaders are small programs that run in the GPU side of the computer, right? So we run our graphics code through our CPU. So first the code is in the memory or the RAM, the random access memory. Then that code or that data that is processed, that need to be processed for showing the visualization of the data. For example, if we have 3 points, that can be a triangle or something else. If we have 4 points, that can be a quad or a square, a rectangle, whatever it is. So we need to translate this numerical data to visual data. And that part is done by the GPU. And the GPU process the data, and the graphics card finally create the visualization and send the output to the screen, right? Because our display or the screen is the place where we want to see our graphics. So like the way we are showing our canvas here on the display, and we want to see what we are drawing on the canvas. So WebGL is derived from OpenGL. OpenGL is Open Graphics Library, a programming language that is dedicatedly created for showing graphics or handling graphics. So shaders are small programs that runs on the GPU side of your computer. And why shaders are useful or powerful? Because shaders can run parallelly. So if you have multiple vertices, for example, if you have a 3D mesh, 3D object with 1000 points or vertices, right? And they have pretty much the same type of operation running on them. So we have some shapes, we have some colors, we have some depth. These are like the simple components of the visual object. So how do we process these things? We can process them one by one using our CPU. So the CPU has usually less than 20 number of cores, right? So it is not very good for running parallel processing. But the GPU has like thousands of core, small CPU that is very weak, not very as powerful as the actual CPU, but that can do some processing very fast, like the matrix operation and other stuff that is necessary for vector operations for graphics. So that's why we have this shader, and we are going to write some code. So there are different types of shaders. We are only going to use two of them, the Vertex Shader and the Fragment Shader. So if you do a quick search in maybe about shader, then you'll see the mention of a lot of different types of shaders, right? So they have Vertex Shader, Geometry Shader, Tessellation Shader, other types of shader. They had a better article, I think. Maybe in a different place. But we are not going to use all these different shaders. We are only going to use the Vertex Shader and the Fragment Shader, which is also, they call it the Pixel Shader, which is more from the GPU perspective. So we are going to use a Vertex Shader and a Fragment Shader, and then we're going to draw our object using this shader. So the first thing, let me define a shader. So the way the shaders are defined in the WebGL code are as strings. So strings can have small code, and that code can be passed to the GPU for processing. So that's why I'm going to create my first Vertex shader. And my Vertex shader is going to be a string. If you look at the book, they have a different format of defining this shader, but I'm going to define them as single string. They actually have multiple lines and they're concatenating the strings. That works as well, but the way I'm doing it is also fine. So this is my Vertex shader, and I also need a Fragment shader, right? So another variable, this is also another string, and naming is Fragment shader. So this name is something you decide, right? So I'm deciding to give this as the names Vertex Shader and the Fragment Shader. I can just say VS, which would be more convenient, and FS or something like V Shader or F Shader or something like that. But just to make it more self-explanatory, I'm using the full name. Okay, so as I mentioned before, you can read up more about this in the book. So the Vertex Shader works for each vertices. So it processes the vertices, it translates the vertices, maybe it does different types of transformation, right? Scaling and other things to the object. So for example, in our case, we have different sizes of the shape, right? So that's practically scaling the shape to make it larger or smaller. So this type of stuff we can do in the Vertex Shader. So the Vertex Shader runs parallelly for each of the vertices and do similar types of operation on each of them. And then the output of the Vertex Shader is converted to a raster image, right? So what we see on our screen is in fact a raster image, which is generated using pixels. So my display here we have a very small number of pixels, right? Very small pixels. So the size of the pixels are very small. We have a very large number of pixels if the display is HD. So the pixels need data to show the color. So that data is generated using the rasterization. And that part is done in the Fragment Shader. So if I use simpler terms, then the Vertex Shader deals with the points, right? So the points or the vertices of the visual object. The Fragment Shader works with the color and the depth. So you define the color and the Fragment Shader process that, and depending on the depth, it sort of create the correct shading of the color, right? It can do some interpolation and it can calculate the value of the color automatically. Okay, so since these are programs, we are going to have some main functions inside. So first thing I'm going to do that. So void then inside the main function we'll write our code, and the same thing goes for here. Okay, and then the next thing is we are going to define the, so you'll see we are going to use locations or points for our shapes. Let me actually first create a shape that we're going to draw on our screen here. So as I mentioned, finally we'll have a triangle here that will be drawn on the screen using the canvas. So let's define a triangle. What I'm going to do, I'm going to do the definition here. First, we need to know the points of the triangle. So let triangle. So this is a 2D triangle, right? And that 2D triangle we can save in an array. So how can we define a triangle? Let me see if I can annotate on the screen. So if I want to have a triangle here, let's say this triangle maybe. I'm going to do a very rough drawing. Actually, maybe they have better things. Yeah. Okay. So if I want to draw this triangle on the screen, so I need 3 points, right? So let's say the first one is P1. And then P2. And then P3. Right? Then let me draw the axis. So this is 2D. So this can be our x-axis. This can be our center. This can be our y-axis, right? This is a very rough drawing. So our center is here somewhere. And then we need to know the coordinate for each of the points. So what can be the first coordinate? So it can be something like maybe, so let's say this is 1, so this can be 0.5, right? So what is the value here? So the value of x is 0, because this is the center, this is 0 0, and so x is 0, and then we can have 0.5, which is y, right? And for this one, let's say this is also a 0.5 for y. So these 2 points are going to be, again, the x is going to be negative 0.5, right? And the y is going to be also negative 0.5 for this one, right? So negative x 0.5 and also 0.5. And this can be positive 0.5. This is also actually negative. This x is positive, this y is negative, right? So now we know our points, we can just use that as variables. How do we go back? Okay. So we are going to use this triangle. So I'm going to just use those points. So I have, let's say, negative 0.5, then negative 0.5. That is the first point. Then yes, we do need to do some sort of scaling, but since we're going to learn more about that, let's assume that our shader will automatically consider everything in between 0 to 1, right? So our center is 0, this is 1, this is 1, this is negative 1, this is negative 1. So for now, in the beginning, we can just go with that concept. You'll see in the shader, everything is normalized using 1. That is sort of the way it works. So the value, the colors, we're going to use in the range of 0 to 1. And whatever scaling you're going to use, you have to do on the base of that. So yes, so 0.5, then next one is 0.5, and then negative 0.5. Then finally, so I'm going counterclockwise. You'll know more about that, how the orientation of the points are going to work. So P2, P3, then finally P1. Then I'm going to do this 0.0 and 0.5. So this is going to be our triangle. And let me clear all my drawings. And before that, let's make sure everything we have done so far, it is fine. There is no error. So I am refreshing the thing and I don't see any error here. So I can assume all the code I wrote so far is working fine. So any question so far before I clear the triangle on the screen? Okay, so I am clearing all the drawing and then we're back to our code. So before finishing this part, this setting up the stage for writing future code part, what I'm going to do, I'm going to add one more line in the shader. And that line is, we are going to define the precision of the floating point variable we're going to use. So why did we create this triangle? Because we're seeing we're going to use floating point. So our shader, we are going to assume that everything is in between 0 to 1. So we need very precise floating point. So for this case, we are going to use medium precision floating point. So this is precision Then I'm going to use medium precision, and then float. So by this definition, you are telling the GPU to use medium precision float. So this is why this is good. So a lot of the device, we can have high precision, medium precision, and low precision. So high precision takes a lot of processing power for the GPU, and many devices that don't even have that type of GPU. So it is safe to stay with the medium, because then a wide variety of GPU is going to support that. Also, if you use low, that is going to be faster, not faster. That is going to be slower actually, because the processing will be slower, but it will be supported with very weak devices, right? Like older computers, integrated GPU, and things like that. But if you have a very powerful GPU, you can go with high P. So I'd recommend using this. We are going to use this throughout our WebGL, just to make sure it runs on all the devices. Okay, and I'm going to organize this part a bit better to make these points look like coordinates. So XY, XY, and XY. So we have 3 points, P1, P2, and P3. Okay, so this is good. And let me quickly refresh it again. And everything's fine so far. We don't see anything because we are not drawing anything yet. After writing our shader, we'll see some output on the screen. So any question before I start writing the shaders and working on the shaders? Okay, so moving on to the shader. So before writing the shader, I'm going to make sure my triangle is working. So I'm going to do a console log, and I'll just print the value. Yeah. And a quick refresh. So I have all this value of the triangles, and I have this canvas. At this point, I can safely remove this test line, and now this is more like a WebGL code. Okay, so what I'm going to do, I'm going to write my lines in the shader now. So as I said, the Vertex Shader is the shader that deals with the points or different. So if you have a triangle, you'll have 3 points, and the 3 points probably have same sort of scaling, translation, and other transformations. So for doing all these things, we don't have to do it one by one, right? Or we don't need to do a serial processing of graphics, which doesn't simply work for graphics, right? When you're playing the game, if you are controlling a character, let's consider that is a human. So if you try to move the human, if one part, so if the human moves pixel by pixel, that will look very bad, right? So for example, the hand is first moving, it is to a different place. It's not simply going to work. That's why we need to do this parallel processing. And that's why GPU was invented, to do very small processing, like this vector processing or matrix processing, but do a lot of them at the same time. So as I said, for example, the NVIDIA RTX GPU, they have thousands of cores, and they can move or process thousands of vertices and fragments at the same time. But that's why we're defining this Vertex Shader. And inside the Vertex Shader, we use our OpenGL or GLSL coding. So the name of the new OpenGL language. So there was some old style OpenGL at some point that didn't use shaders, but the new OpenGL is called GLSL, or OpenGL shader language. SL is for shader language, and GL is the usual graphics library. So we are going to use, there are different types of variables that are used inside the shader. You'll learn more about that, but we have three types of variables. Let me type that in. So we have attributes. This is one type of variable. We can have varying, and we can have uniform. So three types of variables: attribute variables, varying variables, and uniform variables. And then for each of the variables, you can define the data type. For example, let me create an attribute that I'm going to use pretty soon. So attribute, my attribute is going to be vector3 or vector2. So for our case, this is vector2. For next ones, it's going to be vector3. So when you're going to use 3D, for now, I'm going to go with vector2. Also, I can go with vector3, and I can make the third point here as 0. Right? So this is our z-axis. I'm deliberately making it 0. It's the same triangle, just there is no depth in the triangle, right? So if I have this 2D converted to 3D triangle, practically which is 2D, but I'm passing the data as 3D, I can use vec3. And then I'm going to use this position, this variable called a position. Right? So this variable is an attribute variable. So you'll see when writing a code inside the shader, you use this types of standard naming convention, right? So when you're naming an attribute variable, vec3, vec4, or vec2, usually it is prefixed with this a underscore, so that people can see, or just looking at the variable, they can know that this is an attribute type variable. So the attribute type variables are typically here, not typically here, they're here for getting some data from the main code. So if I use a very informal term, then this part of the code is going to run in the CPU side or in the main memory. So the main processor, let's say if you have Windows machine, if you have Intel processor and the main memory, you also have a graphics card, maybe NVIDIA RTX or something, that has also memory inside that graphics card, right? So that is dedicated graphics memory. So this part is going to be processed in the processing CPU and CPU memory side. This part, the shaders, they're going to run in the GPU memory side, right? Inside the GPU. So we need to somehow communicate in this two part of the code. That is going to be a major part of your learning here. You practice more, you'll see how to manage, how to transfer the data from here to here, and then how to process that data. And this concept of running this part in parallel. So if you have a triangle, you have only 3 vertices. If you have a very larger 3D object, that actually can have thousands of vertices, right? And all thousands of vertices, they're going to be processed at the same time using parallel processing in this Vertex Shader. So this concept is the basis of the GPU computational techniques now people use, right? Like NVIDIA CUDA, and there are other GPU, general purpose GPU processing. So originally GPU was invented for processing graphics, gaming, and other stuff. But then people figured out that why we are not using that powerful part of the computer for other stuff like mathematical calculation, research, and other stuff, machine learning. So then eventually they started calculating their parallelized part of the code, the part which can run in parallel inside the shader without any graphical output. And that was making the programs very faster, right? For example, if you want to multiply matrices, there can be 1,000 by 1,000 metrics, and that can be processed inside the GPU. So the purpose of the code is to multiply matrices. There will be no graphical output, but still they are using GPU. That's how the GPU computation came in picture, the CUDA and other programming language. And those languages are primarily developed by the graphics processor or GPU companies like NVIDIA or AMD, right? So these type of variables, they're used for connecting or getting data. We are going to get the position of the triangles. We have three XYZ points, and we are going to get the positions here in the A position. And for now, you're not going to use any varying variable or any uniform variable. You'll see why uniform variables are used later in this code later. So for now, I'm going to complete the shaders. So I'm going to need these positions to send to a defined variable, which is called GL position. This is a predefined variable for Vertex Shader. That works like return. So the GL positions, they're actually processed by the GPU for showing the results. So I'm going to get this A position and putting that in the GL position. But the GL position expects a vector 4. So I'm going to do this casting and making this vector 3 vector 4 by adding one more component, which is 1. So in the GPU, the coordinates are 3D coordinates actually presented using 4 components. So the last one is called X, Y, Z, and W. So this W is something related to homogeneous coordinate system, which you will learn more in the class. So for now, let's just make that 1, just to simplify this. We'll learn more about this later. Okay, so this is done, and we have our triangle and we have our vertex shader. In the fragment shader, we're going to set some color for our triangle, right? So similar to this GL position, they have a return variable that returns the color. That is called GL frag color. And for now, let me use a constant color. Maybe I want my triangle to be red, right? So let's make this red just by putting the red component 1 and the rest of them 0. And the alpha or transparency need to be 1, otherwise it will be completely transparent. So at this point, we have a complete basic bare bone vertex shader and a fragment shader. We are not even using the shader or passing any data from the CPU side, but we do have the shader just to make sure everything is working fine. I refreshed and there is no error. So our shaders are mostly ready for using from the CPU side. So any question at this point?
I have a quick question.
Sure,
Why
go
did
ahead.
you why did you change it from a vector 3 to a vector 4 in the first, like line 7?
Right, line 7. So this GL position, as I mentioned, this is a predefined variable, right? So this variable is sort of when they created the standard for the shader language, the WebGL, they defined this variable as a 4 component variable, right? So the GL position, they have 3 components, right? So it is expecting X, then Y, then Z, and another value called W. So this W is something that is related to homogeneous coordinate system, which is a conceptual thing we learn in the lecture. But the value we set in W here, that is usually going to be dividing these other components, right? So if this is the VEC4 version, this if we convert that to 3D, that would be more like this. Right. That is from a theoretical perspective of homogeneous coordinate. But the bottom line is the GL position, it is always expecting a 4-component variable, right? But for now, our triangle is defined using primarily two values, x and y. Even our z is 0 to make sure that the triangle is flat. There is no z component. But we also don't want to change this to something else. That's why if everything is divided by 1, there is no change in the value, right? Does it make sense? That's why I am setting this with 1, and setting this to 1 will have no effect, or it will not change the value in a triangle. But whatever value I set here, I do need to have 4 components for the GL position and 4 components for the GL frac color. This fourth component, you need to decide how you want to use that. For example, if I make it 0, all the other 3 values will be divided by 0. It will make them 0, right? But if it is 1, then there will be no changes. For the alpha, if it is 1, everything is going to be visible. If I make it 0, the color will not even be visible, right? So you will see more ways to control the predefined variable, but this is sort of the standard that you need to have 4 components for these 2 return type variables.
Okay, that makes sense. Thank you.
All right, no problem. Okay, so any more question about the shaders? Well, so with more practice, you'll have better control over this coding part. But again, just a quick reminder, assume that this is done in the CPU and the main memory side. This is done in the GPU and the graphics memory side. So we are doing sort of this communication in between these two parts. All right, so right now we have this triangle, we have this data, but we need to figure out a way to pass the data to the shader so that we can draw or visually see our triangle here with our color and everything. So the first thing, we need to initialize the shader. So we have the variable defined, but we never use the variable, right? We need to use the variable and make sure they're compiling. So there are functions that helps you to do that. So what I'm going to do, I'm going to use a function called init shaders. Right? And inside that function, I'm going to use our shaders so that the shaders are compiled. And then I want to use my fragment shader. Okay, so where this function coming from? So another thing is when we use some function like this, that is after GL, so that function is coming from OpenGL itself, right? And I didn't use any GL here. So the shader initialization is actually a library function that is given to us by the book. So you'll see, I think this is inside this one. So you can write your own shader processing function. That is, I would say, too much work. No need to do that. Let me do a quick search. So our name of our function is init shader. Okay, it's not here. Probably in another. Yes, found it. So this is the function that was defined inside this Spoon utils. So we are using that library function to compile our shader. So it is expecting 3 parameters. First one is the canvas OpenGL context, which was named as GL here. So we are passing the context here. Then the shaders that we are going to process or compile using this function. So there goes our init shader. Again, we are going to use something like this error message. So if init shader doesn't work, then we are going to say something like failed to compile or load the shader, right? I'm going to say console log inside here failed to load / compile shader. And as usual, I'm going to return this negative one. So just to make sure our shader are loaded properly, I'm going to refresh and see there is no error.